Welcome back to AI Codecast, everybody. You know we love to get our hands dirty with some real algorithms, and today we're taking a deep dive into combination sum 2.
Sounds intimidating, but it's actually pretty relatable once you break it down.
I like where you're going with this.
Think of it like having a bag of coins.
Okay, I'm with you.
Each coin has a different value, right?
Right.
And your goal is to make exact change for a specific amount.
Okay, I see.
But you can only use each coin once.
Ooh, now it's getting tricky. So you're given this set of numbers,
Exactly.
and you need to find all the unique combinations that add up to a target number.
But you can only use each number 1 CE per combination.
Gotcha. So if we had the numbers, let's say 10, 1, 2, 7, 6, 1, and 5, and our target is 8.
Okay.
We need to find all the unique sets that add up to 8 without using any number more than once.
Makes sense, right?
Yeah, it does. But I could already see how this could get complicated pretty quickly.
Absolutely.
Like if we just start randomly trying combinations, we could be here all day.
You're thinking like a true programmer already.
What if we just try like every single possible combination, add them up, and see if they equal the target? It's like trying every single combination of coins from our bag until we hit the exact change.
That's the brute force approach, and it's not exactly known for its efficiency, especially as the number of candidates grows.
Right, like if our coin bag suddenly had hundreds of coins,
Exactly.
we'd be stuck there for ages. So we need a smarter approach.
Definitely. Brute force would just take way too long. It's what we call having exponential time complexity.
Exponential, that sounds scary.
It means the time it takes to solve the problem increases dramatically as the input size grows. Imagine, every time you add just one more coin to your bag,
Oh, I see.
the number of possible combinations explodes. So brute force is definitely not the way to go for larger problems.
Got it. So what's the smarter way to do this? What can we do instead of trying every single possibility?
Well, there's this technique called backtracking.
Backtracking.
Yeah, think of it like navigating a maze. You try different paths, and if you hit a dead end...
You turn around, you backtrack.
Exactly, you try a different route. It's about exploring strategically,
I like that analogy.
instead of just blindly trying everything.
So how does that apply to our combination problem?
We can use backtracking to explore different combinations of numbers, but we'll be smart about it.
Smart how?
We'll abandon any paths that we know won't lead to the target sum.
I'm liking this already. Less wasted effort.
And there are actually a couple of really cool ways to do this using backtracking.
Ooh, I love options.
Let's start by thinking about those pesky duplicate combinations. How can we make sure our algorithm doesn't waste time exploring them?
That's a good question.
What if we grouped identical numbers together?
Oh, so like instead of having all our coins jumbled up,
Yeah.
we organize them by denomination.
Exactly. And we keep track of how many times each number appears.
So it's like having separate compartments in our coin bag.
Precisely. And this brings us to our first elegant solution.
Let's hear it.
Backtracking with counters.
Backtracking with counters.
So we use counters to keep track of how many times we can use each number.
Okay, I'm following.
And we'll combine that with a recursive function.
Recursion, always a fun time.
A function that calls itself to explore those different combinations.
But instead of looking at each number individually,
Right.
we use those counters to guide us.
Exactly.
That's pretty neat. So we're basically saying, okay, we can use this number X amount of times.
Yeah.
And we keep track of that as we explore different paths.
And by doing this, we automatically avoid those duplicate combinations.
Because we're only considering each unique number a certain number of times.
Precisely. It's like having those separate compartments for each coin denomination. You know exactly how many of each you have left to work with.
Okay, I'm starting to see the beauty of this.
Yeah.
So walk me through how this recursive function actually works. What's it doing at each step?
So imagine we have this function. Let's call it backtrack.
Okay, backtrack.
This function is going to keep track of a few things. Like what?
The current combination it's building,
Right.
how much it still needs to reach the target sum.
So like the remaining balance.
Exactly.
Yeah.
And of course, which number it's currently looking at in our list,
Makes sense.
as well as our counter and all the valid combinations it finds.
It's like it has its own little notepad to keep everything organized.
Exactly. So first, we need to think about our base cases. What would make the function stop?
Well, if the remaining sum is 0,
Yes.
that means we've found a valid combination.
Our target reached? What else?
What if the remaining sum becomes negative?
We overshot our target.
You went too far.
We need to backtrack and try something else. Perfect.
All right, so those are our stop signs. But what happens when we're in the middle of exploring? We haven't hit 0 or gone negative.
Well, the function has to decide whether to include the current number in our combination or not.
It's a fork in the road.
Yes. If it includes the number, it updates the combination,
Okay.
adjusts the remaining sum,
Uh-huh.
and moves on to the next number.
And if it decides not to include the number.
It just moves on to the next one without changing anything.
Exactly. For each number, we have these two choices, include or skip.
And those choices are what create all the different paths we explore.
That's a great way to put it.
I like to think of it as a decision tree. Each branch is a new possibility.
And by using our counters and those base cases, we're essentially pruning that tree, getting rid of any branches we know won't bear fruit.
We're being efficient explorers.
Exactly, but you know what's even more efficient?
What? Tell me.
Backtracking with an index.
Hold on. Backtracking with an index. No more counters.
We can get rid of them entirely.
Wait, how do we keep track of duplicates without a counter? My brain is intrigued.
The magic ingredient here is sorting.
Sorting. Okay, now I'm really curious. How does sorting help us avoid picking the same number multiple times?
So imagine this. You have a toolbox, and instead of a separate list telling you how many of each tool you have, you just arrange them in a specific order.
Okay, like all the hammers together, then the screwdrivers and so on.
Exactly. You can see at a glance how many of each tool you have just by their position.
Ah, so by sorting our array, we create this implicit counter. I'm starting to see the light.
Exactly. Let's say our numbers are 2, 5, 2, 2, unsorted. It's a mess.
Yeah, you don't know which two is which.
But once you sort them 2, 2, 2, 5, you can immediately see that if we're at the first two, we can choose it multiple times.
But we only look at the second two if we need to try a different path, right?
You got it. Now, how would this work in our backtrack function?
Well, it probably still needs to keep track of the current combination and the remaining sum.
Exactly. But instead of the counter, we use the current index in the sorted array.
Okay, so the index is like our guide through the sorted numbers, but how do we use it to actually avoid duplicates?
Well, we start at the current index and we loop through the remaining numbers.
Okay,
And for each number, we have our two choices, include it or skip it.
right, same as before.
But here's the trick. We only move to the next index if either. The current number is different from the next one.
So we don't pick the same number twice in a row.
Right. Or if it's the very first occurrence of that number in a sequence of identical numbers.
So like in our 2225 example, we only really consider the second and third twos if we've exhausted all the possibilities with just the first two.
Exactly. We're basically saying, okay, we've tried all the paths using just 1, 2. Now let's see what happens if we use 2.
And we don't waste time trying the second two and then the third two separately because they'd lead to the same combination anyway.
You got it. It's all about intelligent skipping.
Pretty elegant. So how does backtracking with an index compare to our counter method performance-wise?
Time complexity-wise, they both have a worst-case scenario of 2n, where n is the number of candidates.
Okay, so in the worst possible case, we might end up trying all the combinations anyway.
Yeah, but the beauty of these approaches is that in practice, because of the sorting and skipping, it's way faster than brute force.
Right. Practical efficiency is what matters. What about space complexity? How much memory are we using?
This is where the index method really shines. We're not using separate counters, so the main space usage is the recursion stack and storing our results.
So potentially even lighter on memory than the counter approach, but I know everything has its trade-offs. Are there any downsides to the index method?
Well, it relies on having a sorted array.
So if our numbers aren't already sorted, we'd need to sort them first.
Yeah, but sorting is a pretty efficient operation compared to the potential nightmare of exponential time.
That's true. The benefit definitely outweighs the cost.
Yeah.
So you've given us two amazing techniques. If you had to choose a favorite, which one would it be and why?
That's a tough one. They're both super useful. The counter approach is very explicit. You can see the counters updating, which can help with understanding.
Yeah, it's very transparent. Like you can see the logic unfolding step by step.
But for me, the elegance of the index approach wins out. Once you understand how the sorting implicitly handles duplicates, it just feels so streamlined.
It's like having a sleek GPS navigation system versus using a bulky paper map. Both get you there, but the GPS is just smoother.
Exactly. But ultimately, the best choice really depends on your specific situation and preference.
That's a good point. It's all about understanding those trade-offs and choosing the best tool for the job.
Absolutely.
We've covered so much ground today, from brute force all the way to backtracking with both counters and indices.
And hopefully you listeners have a better understanding of how powerful backtracking can be for these combination problems.
If you're up for a challenge, try implementing these solutions in your favorite programming language. You'll really solidify your understanding by getting your hands dirty with the code.
And don't stop there. Think about how you could tweak these solutions. What if you threw in negative numbers? Or what if you wanted to find combinations that were close to the target but not exact?
Those are great exercises to really stretch your coding muscles. That's what AI Codecast is all about, helping you become more creative and confident coders. Thanks for joining us for this deep dive into combination sum 2.
Make sure to check out the show notes for extra resources, code implementations, and more on backtracking and other cool algorithms.
Until next time, happy coding, everyone.